So we're going to have 3 more talks on algebraic complexity and its connections to proof complexity. So the first speaker would be Anamay Tengse from the University of Haifa, and he'll tell us about natural proofs in algebraic.
Thanks, Ramprasad, for the introduction, and thanks to the organizers and Ramprasad and Prerna for the opportunity to present these things here. Okay, so yeah, this is a joint work, or it's a combination of joint works with Chatterjee, who is in the audience and is at Tel Aviv University as a postdoc, Kumar, who is at TIFR, Ramya, who is at MSc, Ramprasad, who is at TIFR, and I'm also here, but from TIFR, and yeah, and I'm from the University of Haifa. Okay, so let's start. Yeah, so if I ask you, are there any numbers alpha and beta for which alpha x plus beta y the whole square, the square of the linear form, is equal to that particular quadratic polynomial? Yeah, good. Can you tell me why? So there is a shorter proof for that. So yeah, basically we have this discriminant law, right? So we know that if it actually looks like this, then b squared minus 4ac would be 0. And you can quickly plug in these values and see that it is not 0. So this tells us that, this lets you sort of prove that, something is not of the kind of, of the type that you want. Let's take a slightly different example. Let's go to cubes of, bivariate cubics. And if we again ask the same thing, does this cubic polynomial look like a cube of a linear form? And now, it's not a popular thing, so I don't expect people to know it off the top of their head. But if I give you this particular equation, so now it's like b squared minus 3ac instead of 4ac. Yeah, and okay, now things have gotten weaker. So we don't have this stronger if and only if condition. We only have in one direction. If it is a cube, it will satisfy this equation. But nevertheless, it still is helpful. We just want to show, we want to use it in this direction. Right? We want to say this is non-zero, so this is not true. And it still works. Okay. And what these things are, b squared minus 4ac and b squared minus 3ac, are equations for polynomials. Okay. And like more pictorially, so let's look at the picture first. So you have some circuit class, let's say the squares of linear forms, or cubes of linear forms. Okay. You have some class of polynomials, let's call it C. Okay. Then a polynomial P, a non-zero polynomial P, is an equation for this class if the zeros of P cover everything in C. And by everything, I mean each instance in each object in C is represented as the coefficient vector here. Okay. So the zeros of P, if they cover all the coefficients of everything in C, then P is an equation for C. And yeah, and cover is the main thing here, because okay, so in case of this quadratics and discriminants, there was nothing in the middle here. Like the zeros of P exactly capture C. But the second example, we don't have this if and only if. We have a weaker thing. Okay, and what we did was somehow stronger than what we need. What we did was I gave you a polynomial and I asked you if it belongs to my class. In fact, we would need something even much weaker. I just will give you a class, and I'll give you an equation, and all you have to do is to come up with some polynomial that is outside my class. Okay, so anything is fine. Not okay. And yeah, just wanted to point out that this thing, even this weaker definition of covering, not instead of capturing, still helps you in doing that. Good. Okay, so these are equations for polynomials. If there are any questions, it's fine. Good. Okay. So what are we going to do with equations of polynomials in this talk? Firstly, we want to see what happens when a class C has equations. How does it help? What does it say about the class? And we are interested in some specific classes. So which classes? I will get to this. And somehow does the complexity of these equations matter? And we'll define what complexity means soon. So yeah, so in an answer to the first question would be something like you'll get explicit polynomials outside of the class sometimes. Okay. And this sometimes it essentially is tying down to the third question, but okay. And we'll be interested in classes that are corresponding to algebraic models, like circuits or formulas or something like that. And yeah, the complexity will matter, as I said, when you want explicit lower bounds using these equations. So, okay, so now we need to define this complexity, right? And yeah, so I'll just give a quick introduction of algebraic circuits so that we are on the same page. I mean, just what is needed for the talk, I promise. Okay. So yeah, so what does an algebraic circuit look like? So you want to build a polynomial starting with variables and some constants on the field, and throughout the talk, just assume the field is complex numbers. That's not, and you will build the polynomial using the basic arithmetic operations of addition and multiplication. Okay, and yeah, so you'll get some sort of a DAG, and there will be a root for the DAG, usually 1. And the polynomial computed by the entire DAG, which will be called a circuit, is the polynomial computed at the root. And it would be, since all our constants are complex numbers, and these are the variables, it would be a polynomial over this field and with these variables. Okay. So yeah, this we call an algebraic circuit for this polynomial f. So the size of a circuit is, so we'll assume that the fan-in is 2, let's say, for every gate. So the size of the circuit is just number of gates. It does not, and it just it's good to check that this roughly corresponds to the number of operations used by C, and I mean, in this case exactly, but yeah, that's it. So now we can define size of a polynomial, which is just the size of the smallest circuit that computes that polynomial. Okay, this is standard stuff in most models. Okay, and we'll also mention formulas. So formulas are circuits where the underlying DAG is just a tree. And yeah, for this talk and in algebraic circuit complexity, what we are interested in are what are called low degree polynomials, where the degree of the polynomial grows polynomially in the number of variables. Okay, and this is good because when we talk about like poly n size, there is only one parameter. Now we don't have to worry about 2 parameters. Okay, so some basic interesting classes and questions in algebraic complexity. So let's have some counterparts to the Boolean world. Okay, so just like we have P or P by poly in the Boolean world, we have VP, which is the class of efficiently computable polynomial families, or just polynomials. And a good example to keep in mind is a determinant. It's not complete in some good sense, but I mean, it's not known to be complete in some good sense, but yeah, it's a good candidate to keep in mind. Similarly, now analog for NP is BNP, and this is a good, this serves as a good analog for explicit polynomials. What you would think of an explicit polynomial is in BNP. So one definition for VNP is that the coefficients are computed by a sharp P machine or a sharp P by poly machine. And what I mean by that is there is a sharp P by, so for my polynomial, there is a sharp P by poly machine, such that if I give you, if I give that machine a monomial, then the output would be the coefficient of that monomial in my polynomial. Okay. And here we have a complete polynomial that is also nice. It's the permanent of, so these are like symbolic, like permanent and determinant of symbolic matrices. And this is complete under this notion of P projections that Marcus was speaking in the morning, but it's basically some notion that is well defined. Good. So the big questions are obviously VP versus VNP. Is every explicit polynomial efficiently computable? Which you can also think of as does permanent. Can you express permanent as some, yeah, can you express permanent as a determinant of not too large a matrix? Okay. Yeah, so this is.
So the coefficients of permanent are computable, so you don't need the sharp in
Sorry.
the coefficients in permanent are computable, so you don't need the sharp.
So for the permanent, yes, but in general, if you give a general polynomial in BNP, yeah, then the best bound that we can give is sharp by poly, and it's also, it goes both ways. Yeah. So let's come back to equations. So just remember this picture. An equation a non-zero polynomial P is an equation if it covers all the coefficient vectors in the class. Okay. And now for this talk, we will assume that the degree and the number of variables is the same. And one good thing that will happen because of this is that then the number of coefficients, which is this n plus d choose d kind of number, it becomes 2 to the order n. So basically now big N is exponential in little n. Okay, so this is all that you need to remember for. Okay, so now we look at equations for little n-variate polynomials, which would themselves be polynomials on big N variable, like big N number of variables. Yeah, I mentioned that equations are useful for proving lower bounds or something. So let's see how. So like in a way that we did on the first slide, right? So if P is an equation for the class C, and if I tell you that a polynomial H does not satisfy this equation, then by definition of the equation, this polynomial is outside your class. So in particular, if your class was VP and your equation was like, it's a good equation, then and you gave me a polynomial in VNP, then you have just proved VP is not equal to VNP. So great. Okay, so here are some interesting facts. So here are some of the best known lower bounds in some structured settings. Okay, and so you don't need to like know all these models. Just there are a lot of structured models that are interesting to the community and they're studied. And most of the lower bounds there are so these are the lower bounds. We have good lower bounds in the structured settings. Structured or restricted, as some people call it. All the above lower bounds use equations. Like everything that I've mentioned here, you can extract an equation out of it. And almost all of them have poly-size circuits. Even the one that does not have, it's like barely, it has a barely super polynomial size circuit. So.
Sorry, about the first line, it's not for a specific dimension. It should be P is an infinite family of equations.
Yes, I didn't want to get into families, but yes, yeah.
So,
okay. So just to confirm, so by family of equations, you mean one for each length of signal.
So what is the explicitness of this P? Or maybe it's not important.
We'll get to that. So the explicitness will come with the constructibility or constructivity will somehow tell you the explicitness of these. And here is another interesting fact. So there are some notable omissions in the list of equation-based lower bounds, and they are the best known lower bound against circuits, against formulas, against determinant against determinant. And none of these lower bounds use efficient equations. In fact, they don't even use equations like these four.
This is a Bauer-Strasse?
Yes.
And it's not.
It uses a dimension of variety, which is not a continuous measure. There is no polynomial that traps it. And similarly, so you use some dimensions of variety or some algebraic kind of thing.
And what is KV?
That is Kumar and Volk. 1.5 lower model complexity. Okay. So now it's a strange case, right? Most of the lower bounds use equations. In fact, use efficient equations. And for general models, we have lower bounds. Okay, they are not great lower bounds, but we have whatever we have. They don't use equations or they don't use, let's say, natural proofs or something. Yes. Okay. So, are there equations for general classes? This should be the first question. And maybe then you can ask for, are these equations explicit or poly-size or something? But are there even equations? It's not clear a priori, as somebody has asked in the morning. Okay, so this is what we want to understand today. So, and this is exactly the motivation behind these works of Forbes, Shpilka and Volk, and this is and Grochow, Kumar, Sachs, and Saraf. Both works came almost at the same time. And they both came, gave the same definition as Marcus had pointed out in the morning. Yeah. So So they define what is called an algebraic or algebraically natural proof. So a non-zero capital N variate, I mean a big N variate polynomial P is a script D natural proof for the class script C. Okay, I've put R here, it should be C. I mean, it won't matter, but so firstly, we'll call it a D natural proof if firstly it has to be an equation. Okay. And secondly, it itself should be computable. I mean, it should be in the class D. So it's like a D constructible proof for C. So D natural proof for C. So any doubts about the definition? And yeah, okay. So you might notice that largeness is missing from here, but as basically because we are dealing with polynomials, the largeness comes for free. A polynomial is non-zero in most places just by default.
So there's some subtle difference between C and capital N, right? Like if C is capturing degree D polynomials, then you need to set capital N appropriately, right?
Yes, exactly. Yeah. So if C is capturing degree D polynomials and N is like N plus D choose B. Right? Yeah, but yeah. So because since we have assumed that G is equal to N, this is right. Yeah. But yeah, good. Okay. So now let's just summarize everything that we have seen in this language. Okay, in the language of equations, natural equations. So equations are useful in proving explicit lower bounds. I mean, if you believe me, they are useful. And at the end of the talk, you'll be convinced that they are. So, and known lower bounds against almost all of these restricted or structured classes, they use VP natural proofs against that particular class. And the general models, most lower bounds against general models, do not use VP natural proofs, sometimes not even equations. So now in this language, the question from the last slide just becomes, are there VP natural proofs for general classes like VP? Okay. So
Question.
Sorry.
Why do we care about this?
Okay, good, because you'll get like, so it's like it seems to be a very natural template. I mean, natural is in the sense of without knowing this template, most people seem to have followed this template. So then it's good to know if the same template would work. Also, in the other sense, if on the flip side, if they don't exist, then it is good to avoid this particular template when you design stuff. And I mean, even beyond all that, just asking for a polynomial that vanishes on a class of polynomials, I think it's an interesting question on its own.
So this question, are the VP natural? So this is a conditional question. I mean, you cannot have for general unless you solve a general lower bound. So I don't understand the last question.
I mean, polynomials exist, but I like just did mention. I mean,
yes.
The question is whether they're in VP or not.
Yes.
Yeah, but how are you going to solve this? If you solve this, you already solved lower bounds.
No.
Yes.
If you answer no, then you solve lower bounds in some sense.
Right.
So even if this is the case, you still need to find a polynomial that doesn't satisfy this equation. That's what gives you the explicit lower bound. At least this is telling you, is this template something that is like,
And yeah, also, I mean, we can prove the existence sometimes without actually explicitly getting a proof. So, like hitting sets, we know hitting sets exist. We just know, we just don't know if they are explicit hitting sets that exist.
But here it's a VP natural. Oh, it's VP is the class you work against, not the.
No. So VP natural. So this class I'm working against.
So if it's VP natural, it would be explicit.
It's constructive.
But I could just tell you that they exist. I mean, this will happen. So for some other class VP, I mean VP prime. So I'll tell you that, I'll prove you that they exist, and I won't be able to tell you what that is. Yeah. So yeah, this is the one question, and I want to split this into two questions because like there are two VPs here. I don't want to deal with both of them at the same time. So, okay, so first, the first kind of questions would be how complex does a lower bound or an equation against VP need to be? That's the moral question that we are asking. It's basically, what is the smallest class D, smallest in some way, such that VP has D natural proofs? Okay. This will be one category of questions that we're interested in. And okay, the work of Forbes, Shpilka and Volk, which introduced the algebraic natural proofs framework, basically is like falls in, like answers a question of this kind. They show that, so there are some classes D, some very structured classes D, like depth 3 powering circuits, depth 2 formulas, and so on, which can't be equations for VP, but I mean, they showed something even stronger. They can't be equation even for depth 3 formulas. So therefore, I mean, they can't vanish over a small set, so they can't vanish over a big set either. This is one kind of questions. The other kind of question is, okay, I mean, if you believe VP natural proof is a general template, natural template, what kind of lower bounds you can prove using this natural template? So what is the best lower bound you can prove using natural methods? So what is the largest, or what are the largest classes C, such that C has VP natural proofs? It's also an interesting question because, and our works answer two questions of this kind. The first work shows that there is an interesting class C, which is like rich enough, for which we have VP natural proofs. I mean, we have equations that are in VP. And the other result says that there is another class C, which does not have VP natural proofs. So it puts a strict upper bound on how large C can get if you want VP natural proof for C. Okay, this is what we are going to. I mean, I'll come to the exact statement. I mean, I'll get more specific about this, but this is the kind of things that we do. And we use classical hardness randomness connections to prove both these results. Yeah.
So because the natural proofs are used in some previous lower bounds, we already had some examples of C that had VP.
Yes,
natural
yes,
proofs, right?
yes.
So it's only interesting if your class C
Is bigger, yes.
is bigger. Okay.
Bigger or incomparable.
Yeah.
Yeah, because the one thing is going to be incomparable. It's good that you're convinced by incomparable. Okay. Yeah, so let me tell you what these things are. Okay, so we are going to like put both these results in these two buckets. I mean, we're going to put everything that we know in these two buckets. And just for reference, so maybe you can look there. Like there are some colors. So, so there is VP and BNP, and so the space, of course, this is like not to scale by any sense of this thing, because VP is a much simpler class than VNP. VNP has permanent, VP is just determinant. So everything that you know, like P by poly, whatever is, everything is between those two circles, those two ellipses. Okay. So we'll put D, for which D has VP natural proofs against VP on the left side, and as you can see. Okay, and this is what you want to answer if D is contained in VP, which means do you have VP natural proofs for VP, or you want to say, do VP natural, is there some VP equation that covers VP? Good. So yeah, as I had mentioned, Forbes, Shpilka and Volk show that D, I mean, the class that has VP natural proofs is not contained inside powering. You need to go bigger than powering, at least, like depth 3 powering, I mean. Something that answers the question in the morning is, I mean, I keep pointing there because they were sitting there. I could not see who that was, but anyway. So, okay, so we know that there is this large class called VP space. It's studied by several works, but it's not that popular. I mean, not right now. Which has natural proofs against, I mean, which has equations for VP. And this basically comes from the fact that if you want to find an equation for VP, it boils down to solving an exponentially large system of linear equations. Okay, and this you can do using P space. So the coefficients are computable in P space. So yeah, this. And okay, so I think this is an overkill. You should not need P space. It's like it's an exponentially large system, but it has a lot of structure, and we should be able to do better. I mean, we should be able to do it. Okay. So these are the results on that side. On this side, so this is the first result that we had. So this is a joint work with all the 5 people. I mean, all the 4 people that I mentioned in the first slide. So we show that, okay, if you look at this class VP prime, which is you take all the polynomials in VP, but you only focus on those that have bounded coefficients. So let's say +1, -1, 0. Okay. And those polynomials can be covered by an equation that is computable in VP. Okay, so a very rich class, and everything is here. I mean, if permanent is here, then it is, I mean, if permanent is here, then VP is equal to VNP. So, I mean, most polynomials that we are interested in are, if they are in VP, they are also in VP prime.
Okay. Equations that you have are not going to be something that is just 0 at all of these polynomials.
0, which
I mean, whatever equation is constructed is not something that's trivially just 0 on all polynomials.
yeah, it's a non-trivial equation. Yeah, we'll come to that. Yeah, of course. There is a very stupid way of vanishing on everything that has these coefficients, but we are not doing that.
What's the underlying field? I guess it's characteristic.
Yes. Yeah.
So for finite characteristic,
We have over finite, right? Yeah. Yeah. But I mean, I won't get into that now. So, yeah. We do. Okay. And
wait, am I misunderstanding something, or can't you just run your circuit on the permanent? Or
we don't have the circuit. I can just tell you that these things exist.
oh, I see.
Yeah.
Oh, I see. Oh.
Yeah. Okay. So the strict upper bound is VNP. If you believe permanent is 2 to the n to the epsilon hard for some epsilon, some constant epsilon, any constant is fine, then VNP cannot be covered using VP equation. So this is some sort of a pseudo randomness or some provable evidence. I mean, from hardness assumptions. Yeah. Okay. So this is like the picture. It's yeah. Yeah.
Are there generic results along these lines that say somehow if you have any fixed class like below VP, you can do some kind of jump and make something that doesn't have those equations in that class. So
Sorry, I don't think I understand.
so is there like, okay, so probably not. So like if you like took a class like subclass of VP, like constant depth formulas.
Okay.
Okay. Is there some way of using the same argument to say, here's a subclass of VNP that doesn't have equations that are constant depth? Or is it just 2 points, VP and V? And I guess the answer is just the 2 points.
Yeah, for now. But yeah, I mean, I can. Yeah, I mean, I think I need to think more about it. So, yeah. Yeah. So it's not like there are too many classes known between VNP and VP space.
That's the problem. Yeah, that's
So, but I think so. So what I mean by that is that I don't think we need the full power of C space to compute these coefficients. And yeah.
Sorry, do I understand correctly? You're saying that there's some polynomial time algebraic circuit such that if I feed it the coefficients of permanent, it will tell me 0 if and only if the VP equals VNP. No.
So if you feed it the coefficients of all projections of permanent or cliff, so everything in VNP. So basically there is no. So sorry, you mean by this?
The bottom.
Okay.
So I don't understand what the bottom one is saying actually then.
Oh, so this is VP. So it's polynomials in VP that also have bounded coefficients. It's a subclass of VPs. It's like it's this guy.
Vanishes on this, but it's still not.
Yeah. It could be that the permanent vanishes. I mean,
Could it be that everything in VNP with
Oh, I see.
one minus one, zero coefficients also vanishes?
On the same equation. So the thing is, okay, this is a spoiler thing. So we have the same result for B and B prime as well.
Yeah.
Yeah. So even all bounded coefficient polynomials in BNP also have equations, but it's not
But
the same.
hopefully
not the same equations.
But it could be the same equations as far as you know.
Yeah, as far as we know.
Yeah. So it doesn't necessarily follow.
Yeah, it doesn't.
You can't control what it does, doesn't vanish on.
Yeah, I mean, we'll see soon.
Just know that it vanishes, right?
Yeah. Okay, so I'll say some things about like each of these results, so that I think it will also clear up these questions. Okay. So the first thing, the equations for VP prime.
I'm sorry, but
Yeah.
can you show that that there are no equations for V and P intersect -1, 0, and 1 coefficients?
No, we show that there are equations for that.
For V and P?
Yes.
Oh, I see also. Right.
So the same technique gives you, yeah, it's reminiscent of some story from mythology. When you try to look for something, sometimes you get things that you don't want. Okay. Okay. Yeah. So okay, here is the idea, and you'll see why these things happen. Okay. So this is what we prove. So VP over this big N variables, they contain non-trivial equations, non-trivial, so that they don't vanish on basically everything for this VP prime class. And how do we construct this? So, okay, for this, I'll need to introduce this definition. I mean, just remind you of this definition of a hitting set. So a hitting set is basically a set of evaluation points that acts as a certificate of non-zeroness for a certain class. So if you give me a non-zero polynomial from the class, then it will not vanish on one of the points in your class. Okay. So, okay, so here is this a very old classical idea that you can do some sort of diagonalization using hitting sets, which means if you find a polynomial that vanishes on everything on the hitting set, you basically have constructed a polynomial that is outside the class because you have diagonalized against every truth table somehow on this. And okay, so the work of Heinz and Schnorr also tells you that there exist efficient hitting sets, and this is just a counting argument. And this is why I mean, and these efficient is also they're also efficient in bit complexity. They are integers of reasonable bit complexity. And the key idea is basically we'll use equations, we'll use hitting sets to construct equations using this diagonalization. Okay, and main idea. Okay, so at the face of it, it's simple. You are constructing an equation. Let it have this following behavior. It takes a polynomial, some polynomial f, and it will output a non-zero value if and only if your polynomial vanishes on everything on the hitting set. Okay, this hitting set is inbuilt in the thing using non-uniformity. Right. Okay. This would work great, but except for you're in the algebraic world, and what it requires is like an algebraic NOT gate, because you want to evaluate the polynomial. If it is non-zero, you want to output 0. If it is 0, you want to output 1. And this is not always doable. You want an algebraic NOT gate. It's a univariate gate that you want to vanish on every non-zero value. So it will have to have degree that is as large as your domain. Okay. So what you do, you come up with some jugaad. You restrict coefficients. Right. You say, okay, I'll restrict my domain, which is why we are in VP prime. Okay. And then you simulate Chinese remaindering, just like simulate going modulo different primes and so on. And you crucially use non-uniformity to do this. So the message is this: if you have efficient hitting set for your class, then the prime version of that class will have equations using this recipe. More or less, almost always this will work. Yeah. So the thing is the number of, okay. So the number of constraints that we are putting on this. So basically, vanishing on the hitting set is a solution to a certain linear system of equations, and forget the exact name, but you can count how many small coefficient, like a small bit complexity vectors will not satisfy this or will satisfy this, and so on. And Seagull's lemma, yeah, that's the name. Sorry, I forgot. Yes. Yes. Okay. So, yeah. Sorry. If there are other questions.
So if you want to tell me it separates VP prime from VP prime, then you couldn't do this.
Not directly, but if you give me a hitting set that does not work for some bounded coefficient polynomial in VMT, then we are done.
Maybe you can do this using a boundary argument.
Not that I know of right now. That seems okay. So some more comments on this. So firstly, as I said earlier, bounded coefficients, it's not a big restriction. Like morally, it's not a big restriction because most well-studied polynomials have small coefficients. Yeah, and does not affect computability. If permanent is in VP prime, then VP is equal to VNP and vice versa. Also, I mean, yeah, I said plus or minus 1, 1, but you can extend it to 2 to the order n for. It will affect the size of the equation that you have because you have to vanish on the domain and so on. So good. Yeah, and also, so this follows from some other like notions of universal circuits in algebraic. Yeah. Okay. Yeah. Thanks. So making this work, if you make this work for a large enough bound, like with integer coefficients, but a large enough bound, like 2 to the barely super polynomial, then you would show that all of VP has VP natural proofs. Okay. So it's not like if you are working with bounded coefficients, then you can't do anything. You maybe can. Okay.
Also, no, right? Existence of VP natural proofs against.
Yeah, I mean that is so the existence part comes because we use existential hitting sets. But if you do this using some constructive way, then you are done.
What do you mean by it does not affect computability?
Yeah, because the restriction of, I mean, how you go from VP to VP prime is by restricting the coefficients of the polynomial. You don't care how large the constants are that are required to compute it.
Does the same proof give it, you're claiming they're VP natural, but aren't they gonna be in a much smaller class?
They are. So they are like depth 4 circuits or something.
Okay.
Yeah. Yes. Yeah. Very good. Okay. Yeah.
But we should somehow like impose a rule that there's some natural classes that correspond to family polynomials. That's not the case.
Sorry.
So like when you consider a family of polynomials and you try to find hitting sets with natural proofs against, I mean, it should like the interesting cases are where these polynomials correspond to circuits. Yeah.
Yeah. So that's not true for this because I mean it has to be closed under projections or something. And if you substitute it does not have that property. Yeah, but I can say something else about it later maybe if there is time. Okay. So yeah, as we had mentioned, like since VNP also has efficient hitting sets, the same thing goes through for VNP prime. Okay, but at the same time, if you find a hitting set, okay, for which let's say permanent like the hitting, I mean the permanent vanishes on the hitting set or something or some other polynomial VNP, then you have found a VP natural proof for like the separation, not just for VP, like a proof that witnesses the separation that you want to witness. Okay, so now let's get to the other thing. So no VP equations for VNP, and this no, the star is for because there is an assumption on the permanent hardness of the permanent. Okay, so how do we do this? So basically, this starts from the other direction of hardness randomness connections. Hardness gives you pseudo randomness, and this is the machinery of Cabinets and Impaglia. So from 20 years ago, almost now. Classical result. So how does this machinery work? It needs 2 things. One, you need, let's say, an exponentially hard polynomial, and you need some combinatorial design. You plug these 2 things into this, it gives you a hitting set for VP. And now notice that, I mean, so the parameters have been set such that this little n, so if the hardness is exponential in this little n, then the hitting sets are for 2 to the like poly in 2 to the order n. Sorry, poly in 2 to the n. Okay. And hitting set, just the definition is there. Okay. So now here is what we do. So we say, okay, so we observe the following. So if this exponentially hard polynomial also happens to be in VNP, and if you are careful about your choice of combinatorial design, in particular, if the design is based on Reed-Solomon codes, then this entire machinery, the computation somehow becomes VNP succinct, for whatever that means. And I mean, the important part about what that means is that the hitting sets that you got for VNP for VP of capital N, they will look like coefficient vectors of little n VNP. Okay. So yeah, and because of the definition of the hitting set, this now shows you that if the permanent is, if this object exists, then there are, and then the coefficient vectors of VNP are a hitting set for VP. So they can't be, VP can't be an equation. So I'm slightly short on time, so I'll just move on. And okay, so some comments about this, because this is a, I mean, yeah, this is quite an interesting result, even though it is apparently simpler to prove. Okay, so what this means is that if you now show existence of any VP equation for VP, then you know that equation, of course, subject to the permanent being hard enough, will witness the separation of VP and VNP. This is just brilliant. I mean, this basically says, would say that if VP and VNP are sufficiently separated, then there is also an algebraic natural proof that witnesses the separation. Okay. And okay, so something to note is that the coefficient vectors that we generate here have large absolute value. They look like 2 to the poly n. So they are not in VNP prime. So we are not contradicting the hardness of permanent here. So
why is this give you that you are separate from closure? Because I want a natural proof give you a separation from closure.
yes, but then also, I mean, yeah, also that.
But you're only assuming the permanent is not going to be getting the permanent is not going to be closure.
We are assuming the permanent is exponential. I mean, we are assuming something stronger. It's that it's of the sort that what should I say? I mean, if the lower bound is not lower bound, if the hardness is large enough, then there is an algebraic proof or something. So,
but you don't actually get this not the closure.
No, but that's, I mean, if you assume that there is a VP equation for VP,
Yeah.
and you know for a fact permanent doesn't satisfy the equation, so you also get that permanent is not in the equation.
So
No. So if the permanent is hard enough, and you know that there is a VP equation for
I mean, you need that. I mean, if
the permanent is not.
I mean, this assumes that there is a VP equation for VP, which we don't know. I mean, yeah. And this, okay, so it also gives this very nice. It's a very satisfying sort of statement. It tells you that if you have an efficient equation for some class, then you have an explicit object outside that class. Because efficient equations don't vanish on all explicit coefficient vectors. And of course, subject to permanent being 2 to the g and 3 epsilon hard, but I guess everybody believes that. Okay, so there are some open directions. These are mostly probably interesting to algebraic complexity testing, but yeah, I mean, hopefully some of them will be interesting to a larger people. Yeah, so one thing is you could, so if you believe that there is a barrier, like there is an isolation barrier in the sense that you believe that there are no VP natural proofs for VP, then maybe you could try to extend what we did for VNP to VP as well. In particular, if you want to follow the same recipe, it will need sort of a VP succinct analog of the machinery of carbon and in Pagliazzo. And just that, even if it does not work with poly and hardness, just that by itself will be highly interesting object. Because so it looks like directly extending that work will be quite a tough task. But still, I mean. Okay. On the other hand, if you believe that natural methods are sufficient or something, then maybe conditionally extend the first result that I spoke about, to work for larger coefficients, maybe 2 to the super poly n, or even because of the second result, as I mentioned, the coefficients are 2 to the poly n large. So now even if you show that for polynomials in VP that have 2 to the poly n size coefficients, if there are equations for them, then you know that VP and VNP can't be the same. Of course, but this is more of the first bullet on the last slide. Okay. And yeah, that's about it. So,
Can you go back? Can you say something about why VP succinct analog of KIL3 would be interesting in its own right? Can you get like reconstruction out of this automatically?
I mean, okay, so why I mentioned that is just because so we basically have two methods of going from hard polynomials to hitting sets in algebraic complexity, and only one of them works. It's like one of them is a low degree. So the other thing, the other GKSS generator is it requires a univariate polynomial that goes into it. So if you try to do what we do in our case, you get some high degree equations. So it's not necessarily VP succinct or VNP succinct. So I meant that. I mean, so basically any new way of going from hardness to randomness will be interesting in its own right, firstly. And if it can work with poly and hardness and still give you that would be.
Other question? If not, then